Huffman codes. Alright, so this problem has to do with storing data. So suppose you have a file that uses ASCII codes. So every ASCII code has the same length. It's usually 7 bits, although some people model it with 8 bits. So to calculate how much you need to store it, you just count the characters and multiply it by 7 or 8, depending on whether you think it's 7 bits or 8 bits. So the ASCII code doesn't really optimize for some symbols are used more than others. Now if you think of something like Morse code, then that one takes into account what things are used more than others. So for example, the letter E in Morse code is just a dot, whereas the letter X is dash, dot, dot, dash. So it takes into account that some things are more likely, so you should just need like a quick symbol for that, and others are less likely, so you need more to represent them. So suppose you have a file of characters. Can we come out with a coding scheme so the number of bits required to store them is minimum? Okay, so what we're going to do is we're going to build an optimal code that has something called the prefix property. So the prefix property is that if you encode something, like say if A is 0, 1, then no other letter starts with 0, 1. Because then if you have like code that goes like that, you would want to know that this is an A as opposed to this being a B, you know. So you want to be able to read it off, boom, it's this letter, it's this letter. So that's the prefix property. There's, like, if you have something that represents a letter, it's not a subset of anything that represents another letter. Alright, so no letters can start with 0, 1 if A is 0, 1. Okay. Alright, so basically, if you want to optimize the storage of some thing you send, so suppose you have a bunch of symbols, and then the weights, so the number of bits for a particular symbol and then the symbol appears f of I times. Right, so basically we want to take into account how often do you need this symbol and how many bits you need to represent this symbol. Then the total number of bits used would be the sum over all the symbols of f of I times w of I. Right? So each time it appears, you multiply by this number of bits, and you have this sum. For example, with the ASCII code, all the weights are 7s. So you just have 7 times the number of times it appears. Okay? So let's do an example. Suppose you have a file that has that frequency. So A appears 10 times, E appears 15 times, O appears 12 times, S appears 3 times. T appears 4 times. A blank appears 13 times, so that's a space. And a new line appears once. So you have this short file is basically a paragraph. At the end you click enter and you have a new line. Or maybe 2 paragraphs, whatever. And we want to encode this. So if we used ASCII, the cost would be 7 times 10 plus 15 plus 12 plus 3 plus 4 plus 13 plus 1, which is 7 times, I think the sum comes out to 58. And that's, I think, 406. If you're a bit more clever, you could do 3 times that sum. So what do we mean by being a bit more clever? Well, we only have 7 symbols. So we could use a binary encoding. Right? So by using binary, we could represent it this way. Now, the cost of binaries, I'm not sure you can get away with it, and the prefix, you could probably still do it. Yeah, so like if you think in binary, you have, yeah, it's fine. Yeah, you can definitely do that. So there we have 8 symbols, right? And here we just have 7. So you could call this A, E, O, S, T, D, L, in new line, and you could store it with just 174 bits. Right. But there is an even better way to do it, and that's going to be the Huffman code. Okay, so here we're going to try to take into account the fact that they appear at different frequencies. So for the Huffman code, you need to do kind of 2 steps. So step 1, you create a tree. So you start with the nodes being A, E, and you keep track of both the letter and its value. Okay, and then you check the numbers and you grab the 2 smallest ones, which are 1 and 3, and you link them together and add the numbers. So now with what you have left, you look at the 2 smallest numbers. So this guys get erased. So you have 10, 15, 12, 4, 13, and 4. And you can see the 4 and 4 are the smaller ones. So you add those 2, you get an 8. I'm gonna not delete them, but you stop the things that are already in edges, you stop considering them. So the next two smaller ones are 8 and 10. And then the next two smallest ones are sorry, 8 plus 10 is not 10, it's 18. So this is 18. So the next two smallest ones are 12 and 13, which I'll put over here. Alright, so we've used this, okay, so what are the two smallest ones now? I guess it's 15 and 18. And now the two smallest ones are 25 and 32. Okay, so this biggest guy is the sum of all the guys. Okay. So if you add up 10 plus 15 plus 12 plus 3 plus 4 plus 13 plus 1, you get 58. So if you do this process right, the root will have the sum of all the frequencies. Okay, so then we're going to clean up this tree. I mean, obviously, if you're coding it, the computer will be able to analyze the tree on its own. But for us to see it better, it helps to think of it as you have 58, 33, 25, 33 goes down to 15 and 18, and 15 is attached to the letter E. And then the 18 goes down to A, which is 10, and 8. And then 8 goes down to 4, which is T, and another 4. And this 4 breaks down into S. And L. The 25 broke down into 12 and 13. The 12 is O, and the 13 is BL. Okay? And then, I guess that 2. And then step 3 is label it. So we have 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. Alright, so then the idea will be so the letter E will be associated to 0, 0. A will be 0, 1, 0. O will be 1, 0. BL will be 1, 1. T will be 0, 1, 1, 0. S will be 0, 1, 1, 1, 0, and NL is 0, 1, 1, 1, 1. So I don't get the same ones the notes get. I'll tell you why, but in a bit. But let's see how much this would cost. So E appears 15 times, and we need 2 bits. A appears 10 times, and we need 3 bits. O appears 12 times, and we need 2 bits. Blank space appears 13 times, we need 2 bits. T appears 4 times, and we need 4 bits. S appears 3 times, and we need 5 bits. And new line appears once, and we need 5 bits. So we're multiplying the frequency times how many bits it required, and if you add these up, you get 146. So I don't get the exact same labeling that that the notes have, but I get something that has the same cost. And that basically just depends on how you order things here. So if I had drawn, when you clean up the tree, if I had done it a different way, so let me think one way to do it. So let's kind of put them in order from smallest to largest. So after 3, oh, there's also a 1. So this will create a 4. And then these 2 create an 8. And then the next one was 18. But 18 then mingles with 15, so I'll put 15 here. And then I'll put the 12 and the 13 over here. So if you draw the tree that way, oh, isn't it the same tree? Yeah. So they both are the same tree, right? The only difference is that over here, if you go 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, maybe I'll put these zeros and ones in a different color so that they don't get confused with the names of the vertices. So the labelings look the same, but one difference is that here I put the 15 on the left and the 18 on the right, whereas here the 18's on the left and the 15's on the right. So you, depending on how you draw your tree, you're gonna get different names at the end, but you're gonna get the same weights because the paths will be the same. Like this path takes 4, whether you label it as 0, 0, 0, 1, or like over here, you label it 0, 1, 1, 0. So you can get slightly different answers and still be the same optimal path. So this Huffman code, what it does is it optimizes how many bits it needs to store a file. So here it lowered down from 174 to 146. So the binary one gets you 174. This one gets you 146. And it turns out that computer scientists have proved that this Huffman code gives you the optimal one. So why is this in the greedy algorithm section? Well, it's kind of greedily choosing these guys. So it's like if you need very few nodes to get to something, then you should use the least number of characters. And if you need a bunch of nodes to get to something, like to ML, you have to go 5 edges, then you will need 5 bits. So you choose to label things so that the things that appear the most will use the least number of characters. Now, if you just do it randomly, well, not randomly, but if you just do a naive greedy algorithm where you're like, well, E is the one that appears the most, BL is the one that appears the most after that. Oh, actually, I guess it does work out. So the one that appears the most needs 2 characters. The one that appears second most needs 2 characters. The one that appears third most still needs 2 characters. The one that appears fourth most needs 3. And then you get 4, 5, 5. And so you could greedily determine what order it'll be and the number of bits they need. But how do you create the bits that are prefix good and that you're still able to store everything? And that's why the Huffman code is it's combining greedy with a process that gives you what you need. So if you look at the notes, they're in Moodle already. There's code you can do to write it. The data structure that you use to write this is a heap. You could also do it with a tree, but this pseudocode is for a heap. And then the complexity is linear. So I think overall is n log n. So building the heap is big O of n, and then the number of roots is big O of log n. So then the total number of operations is big O of n times log n. Okay, any questions on greedy algorithm? Yeah.
Wait, why wouldn't it be n plus log n?
Let's see. Good question. All right. Well, I guess you have to call it for each element you have. Yeah. And determining its number of bits for each element is log n. So you do n things log n times. Okay, so the next section is graphs. This is chapter 7 stuff. Not that we have a book, but lecture 7 stuff, I guess. So, did you see graphs in 317? Yeah, so you're all familiar that a graph is a set of vertices and a set of edges. Yeah. Okay, so an example of a graph. This would be K4, the complete graph on 4 vertices. Definition here says a graph is a finite set of vertices and a finite set of edges. You don't need them to be finite to be a graph. So, but obviously in computer science we use finite graphs, but the definition doesn't have to say they're finite. Okay. There's also the notion of directed graphs. So in a directed graph, the order, so the edges have a direction. So this edge and that edge are different. Whereas in a normal graph, if you just have the edge, they're connected in both directions. But sometimes in the real world, we have directed edges. If you're thinking of all the airports in the US and a flight from one airport to the other, there doesn't always exist a flight back. Although it's usually that way because of logistics. If you're a pilot that lives in Atlanta and you have a flight to Chicago, you want to get back to Atlanta. So usually those flights go back and forth. Yeah, that's.
So when you say complete graph, is that just the graph where every vertex has like edges to all the others? Or
For every pair of vertices you have an edge.
okay.
Yeah, the way you phrased it's also correct. Every vertex is connected to every other vertex. A vertex is in a complete graph. You don't have an edge between a vertex and itself. But in general graphs, you do allow loops, things to be connected to themselves. Okay, so if you have a graph then if you just select a subset of these guys, then that's a subgraph. So the more natural ones are like, for example, that's a subgraph. So you pick some vertices and some edges, and that's a subgraph. So it's like you can delete edges, but you cannot add vertices. You cannot add edges. If you add any of those two, then you're no longer a subgraph. What else? Let's see. What other definitions do you need to know? Alright, so a graph is connected if for any two vertices in the graph there exists edges connecting D1 to D2, So for example, this guy is connected. If you're thinking from 1 to 2, you just have that edge. From 1 to 3, you can connect this to 2 and then 2 to 3. If you want to go to 4, you can just go 1 to 4. If you want to go to 5, you go 1 to 4, then to 5. If you want to go to 6, you do 1, 4, then 4, 6. If you want to go to 7, you do 1, 4, 4, 6, 6, 7. If you want to go from 3 to 7, you do 3, 2, 1, 4, 6. So if you pick any two vertices, there is a path from one to the other. If I say delete this edge here, then it stops being connected because there's no way from the guys here to get to 6 or 7. Okay? So this is an example of a graph that's not connected. All right, a cycle in a graph, it's pretty obvious. That's a 3 cycle. That's a 4 cycle. 5 cycle, and so on. So a cycle is when you can reach yourself again by following edges. So a tree is a connected graph with no cycles. Something like is that legal? No, that is not legal because then you have that cycle. Okay, so that's an example of a tree. They look more like trees if you put the root at the bottom. Looks a bit more like a tree. So connected graph with no cycles are trees. Alright, so here's a theorem. If we add an edge to a tree, we get a cycle. So suppose we have the tree with vertices B1, B2, Bn. And then suppose we add an edge between Vi and Bj. So if I want to draw an edge between two vertices, I'll represent it by the pair Vi, Vj. So a pair of vertices determines an edge, right? So if I want the edge between 3 and 6, I could call this edge 3, 6. All right, so suppose we add an edge Vi, Vj. By definition, a tree is connected. So there is a path from Vi to Vj. So you can imagine you have a path from Vi to Vj. But if we add the edge Vj to Vi, we have a cycle. So, proof complete. Alright. So trees are kind of special that way. If you add an edge, you always get a cycle. Alright, so another nice observation is if you remove an edge from a tree, it is no longer connected. So if you think of, say, this tree, if I remove this edge, then this dot is isolated from the rest. If I remove this edge, then these two are isolated. If I remove that one, this is isolated. If I remove this one, this whole part is isolated. Right? So the tree is kind of like, kind of optimal in a way. It's, if you just add one more edge, you stop being a tree. If you remove one edge, you stop being a tree. So it's a pretty special object in that setting. So let's prove this. So I guess here we're going to remove Vi, Vj. And what's going to happen is that now Vi and Vj are no longer connected. So claim Vi and Vj are no longer connected. Okay, so before we remove Vi and Vj, well, suppose they are connected. So you have some path that gets from Vi to Vj. But then what happens? Well, if this implies that when Vi was connected to Vj, we had a loop, but we had a cycle. But that's impossible in a tree. So if there's a path from Vi to Vj, then before you remove this edge, there was a cycle. But if there was a cycle, then it wasn't a tree to begin with. So again, there's these two nice properties that trees have that we're going to use. We'll use these properties next Wednesday because we don't have enough time today. We'll do a bit more today, but not enough from that. And but these are two observations we're going to need. So there's an algorithm we're going to learn. It's called Kruskal's algorithm. And the way we prove that it's optimal is using these two theorems. Yeah, so just a few more notes. A weighted graph is a graph where each edge has a numerical value to it. So normal graphs, you think of all the edges as equally valuable, but in weighted graphs, you can put numbers on them, and it represents that they're more valuable or more costly. And so if you're thinking of, say, the airports, and you have a flight from one to the other, the number could represent the cost of the flight, or the miles, or anything you will want to analyze. Okay. So so a minimal spanning tree is a subgraph that is a tree whose weight is minimal. So a problem that computer scientists often try to solve is you have a graph and you want a minimal spanning tree. So again, why would you care, for example, if you have all of the flights? And so a minimal spanning tree gives you a way to connect from any city to any other city. And if your weight is price, then you kind of figure out what's the least amount of money you can have to get from anywhere in the country to any other place in the country. Right? So finding this minimal spanning trees is pretty useful. And then we're going to learn an algorithm called Kruskal's algorithm, which is basically the greedy algorithm for this problem. And we'll learn it next Wednesday because Monday you have your midterm.
Mm-hmm.
Okay? All right. Any questions about the midterm? So it's just what I talked about on Wednesday, a true-false section, radix sort, greedy algorithm, sum of primes algorithm, Euclidean algorithm. What else did I say? Egyptian fractions. Yeah, that's the greedy part.
Master theorem. Master theorem.
The master theorem. Yeah, there will be a problem where you have to use the master theorem. There's a problem where you have to do radix sort. There could be a problem for quicksort. Could be a problem about writing a prime and the sum of two squares. Could be sub-problems on that, like finding t such that t squared is negative 1 mod p. Questions about the Euclidean algorithm. I feel like I'm missing something that I said last class. No?
The puzzle is the other thing.
Oh, the puzzle.
I thought you just said that would be on the exam.
That won't be the exam. Yeah.
And then didn't you also say we won't have to do quick sort by hand before to just
I
understand?
did say that, yeah. But I could ask it as explain the algorithm. Yeah.
There's also the number of versions.
That's right. There's another one I could explain. I could ask as explain the algorithm. Yeah. So pretty much anything that was asked in homeworks 4, 5, or 6, you can see in the midterm. I don't really ask anything that's not in there. I mean, some of my questions would be conceptual versions of the ones that are in homework, right? Like if I ask, explain how quicksort works, that's different than in the homework where it's code the quicksort. In the exam, you don't have time to code it, so you just explain what would you do to code it. Yeah. But I didn't choose any problems outside there. Now in the true false, maybe I'll go a bit outside, but they will all be related. Okay, so have a good weekend. And I'll see you on Monday.